Hello. Welcome to my P2 health session. And okay, so since this is a little bit delayed, let's just begin with our homework 2 health session. So basically in this homework, you are going to perform cryptanalysis of 4 different ciphers, which are the Caesar cipher, also known as the ROTX cipher, and a fine cipher, a Vigenère cipher, and the substitution cipher. Okay, so the first thing I want to mention is that unlike homework 1, homework 2 is completely platform dependent. So you'll be working with C instead of the x86 assembly. However, you still need a Linux environment, so for Windows and Mac users, you can install Docker Desktop and run Linux. So basically all you need to do is head to the link below and follow instruction. This is the official website. And just follow instruction to install the Docker Desktop. And for this homework, you only need to edit a file called CS642-cryptanalysis-implement.c. Yeah, so this file includes 4 functions, which are CS642 perform blah 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 analysis that you need to implement for the 4 cipher that I just mentioned. And there are also 2 optional functions that you can choose to implement or not, depending on how you implement your code. So the CS642 student init is for your initialization code, and cleanup is for cleanup code, and they are both optional. Finally, I want to note that, so that's here's the homework criteria. You can get a bunch of free credits just by, making sure that your code compiled and making sure that your code have good comments and no segfault happens. If you've done all these simple challenges, then you can get a minimum of 25 points. And I'll also grade your homework based on how you implement your cryptanalysis, as well as how successful your attack code can recover the plain text. And also, no report.empty this time, so you don't need to spend a lot of time writing the stupid stuff. So as long as your implementation points toward the right direction, you are going to receive full implementation credits. Also, you can receive full credits if your implementation works all the time, and partial credit if your implementation works sometimes. And finally, for the substitution cipher that we will mention real quick, if your decrypted plaintext looks quote-unquote good enough, like there's only 1 letter off, then I will also give you full credit for that. So rest assured, if your substitution cipher doesn't work 100%, but it is able to generate good enough plaintext, then I will still give you full points. So any questions about the criteria? If there's no question, then let's head to the 4 ciphers that you will need to perform cryptanalysis on. So let's begin with the ROTX cipher. So ROTX cipher, also known as the Caesar cipher, works by rotating every letter in the plaintext by a fixed amount. For example, if the key is 13, each letter is shifted forward by 13 positions in the alphabet. And if the key is 13 in our case, and this is called the ROT13 cipher, or Caesar cipher, which was a cipher invented by Julius Caesar. But generally speaking, even if X is not 13, we still refer to it as Caesar cipher. So you can take a look at the example. So you can see that for the string hello, the H is replaced with U because H, the opcode of H is 1, 0, 1, 2, 3, 4, 7. And 7 plus 13 is 20, and the opcode of 20 is the U itself. So for any H that it encounter, it will get replaced by U. And for any E encounter, replaced by R because of the same reason, and so on. So we can see that RTX cipher is pretty straightforward. And since there are only 25 possible shifts, this makes a cipher extremely easy to break. So, because there are only 24 possible keys, you can simply just try all of them, right? And yeah, this is called brute force attack. So we basically just decrypt the text using key from 1, 2, 3 to up to 25. And then we determine which decrypted text looks the most correct. Yeah, that's basically all you need to do. Yeah?
Wait, so are we decrypting or encrypting?
Decrypting. Yeah. So this is about decrypting ciphers and recover its plain text. Yeah. All right. But the real question is that how do you determine which decrypted text is a real plain text? That's a real problem. And to determine this, the homework provides you a word dictionary. And this dictionary is generated from the exact same text corpus your plain text is generated from. So if words from the dictionary appeared in your decrypted text, then we can safely assume that the plain text is more likely to be correct. So our goal is to assign a score to each possible decryptions. And then the more dictionary word it appears in your decrypted plain text, the higher the score is. And the more common a specific word appear in the text corpus, the higher the score should also be, right? And we basically just evaluate your plain text according to that score. And if we pick the highest score, then basically that plain text is probably the original plain text. Yeah. So, so let's get to the dictionary structure that I just mentioned. So this dictionary is stored as a word string and a count, which stands for how many times the word appeared in the text corpus. And basically, there are some functions that allow you to query that structure. And these are two functions that can help you do so. First, the CS642 get word dict size function returns the total number of words in the dictionary. And the CS642 get words from dicts will return the word dict structure for the corpus. Using these two functions together, we can get the size of a dictionary, and we can loop through every word and use them to look up the word count. However, one damn thing about it is that this is an array structure, not something like hash. So for better performance, you can implement your own data structure based off of these provided functions, such as a hash table. And doing so may help you improve lookup time significantly. But yeah, unfortunately, you need to implement that yourself. But of course, feel free to implement however you want, as long as your code can finish in a reasonable time. Hash table is just how I implement it to get a better time performance. All right. Now here comes the most important thing about this homework is how do you come up with the score that can help you determine how English-y or English-ish it looks like. So we'll be using a technique called the log likelihood score. So instead of like counting the number of words, we can calculate the likelihood score by for each of a word in a decrypted text. Like if a word appears in a dictionary, then we add the log of count to the score. So this is a pseudocode about how this is done. Basically, like changing from adding counting like the number of words appear in your plain text to adding the log of a count of a word appearing in plain text. And the reason why we do that is that the word count itself is like the logarithm. So like how to describe it. So like if we do a sum of logarithm, then it basically acts like probability. And this can kind of help you prevent huge counts from dominating your score. Basically, we're doing probability multiplication, but taking logs on the equation, which becomes addition of logs. And at the same time,
So I'm kind of confused as to why we can't just find like the maximum word count.
Yeah, you can do that, but this is a slightly better scoring function. Because if you're going to use plain word count for substitution cipher, then it doesn't work as great compared to this log likelihood criteria. Yeah, and there's also an added benefit of like preventing buffer overflow. Not buffer overflow, sorry, integer overflow, because we can avoid, because we're adding a log, so log grows slower. We sort of nerf the large word count, and Anyway, after calculating the score of all these possible decryptions, we basically just choose a text with the highest log likelihood score. And that text will be extremely likely to be the correct or original plain text. And this works extremely well because the scoring is evaluated from the exact same corpus that the plain text is generated from. And this works better compared to using stuff like n-gram, which is kind of standard in CTF crypto problems, because usually they don't provide you a text corpus. But since we have the text corpus, this method is probably the best one that I can think of. Yeah, but of course, again, feel free to implement your own scoring function as long as it is reasonable, and that your code can finish in a reasonable time and your attack work as intended. Yeah. All right. So, any questions so far regarding the RTX cipher? Okay, so in summary, just brute force, and then calculate the log likelihood and pick the highest log likelihood to be your decrypted text. Yeah, that's basically what you need to do. All right, now let's talk about task 2. So for task 2, you need to break the affine cipher. So this encryption method encrypts each letter for awfully plain text using a specific linear function. In other words, every letter is transformed linearly according to some linear algebra. And the rigorous math formula is pretty simple. Basically, it just does ax plus b mod m. And basically, the encryption algorithm is a one-dimensional linear function under modulus m. And in our case, we're working with m equal to 26 because there are only 26 letters in the English alphabet. So here the value of a can only be chosen from the odd number between 1 and 25. And this is because a must be relative prime to 26. If you've taken some kind of number theory 101 courses, you know that a needs to be co-prime with 26. So a can only be chosen from odd numbers between 1 and 25. The value b, on the other hand, can be any number from 0 to 25. Again, because these values work under the module of 26. Here's an example of a affine cipher. So in this case, a is 5 and b is 8. And the linear function is 5x plus 8 mod 26. So first turn the alphabet into numbers from 0 to 25, where a is 0, b is 1, and so on, all the way to Z is 25. And then we apply the linear function, module 26, to get a result that lies in the range of 0 to 25, and then convert them back to alphabets. So for the letter E, for example, it first gets turned into 4, because E is the fifth number. And 5 times 4 plus 8, mod 26, is 2. And 2 is like a third letter, which will get turned back to the letter C, and so on. So basically, this is pretty similar to the RTX cipher. The only difference is that there is a constant A before X. So if A is 1, then this is basically RTX cipher. And because there are only 338 keys, because there are only 13 possible values of A and 26 possible values of B, this means that there's actually a very small number of possibilities. So you can use the same technique called brute force to try all the 338 keys until the correct one appears. Yeah. And same question. So how do you make sure that the decrypted plaintext is what we want? And the answer is exactly the same as what we're going to do with the RTX cipher. Yeah. So any questions so far? Yeah.
How do we make sure there's no collisions like after we do the AX plus B? Could there be two characters that map to the same cipher?
In our setting, this is actually no, because we make sure that A is a odd number, not an even number. If A is an even number, this might happen. But actually, 26 is 2 times 13, right? So just make sure that A is not a multiple of 2, then you should be good. And also, maybe we should also make sure that A is not 13, to be honest. So maybe like I was wrong about A. A should also not be 13, yeah. And just to make sure that A and B, not A and B actually, you need to only care about A. Just make sure that A is co-prime with 26, and that's all you need to do, yeah. So usually, an ideal scenario is that we want to make sure that M is a prime number, because if M is a prime number, then any of the element will become a generator. Yeah, but since there are 26 letters, we can only make sure that A is co-prime with 26. Yeah. Yeah, so in summary, what you need to do for task 2 is exactly the same as task 1. Brute force all possible A and B's, and use the log likelihood sum to find the plain text with the highest score, and then basically return that plain text and the corresponding key. And that's pretty much all you need to do. All right, let's move on to the third cipher, which is a Vigenère cipher. The Vigenère cipher is an encryption method that improves on simple ciphers like a Caesar cipher by using a repeated keyword to shift a letter in the alphabet. So what this means is that instead of shifting every letter by the same amount, the Vigenère cipher uses a different shift for each letter with some sort of repetition. So basically, this is how it works. We first choose a key, which in this example will be apples. And because the plaintext message will pretty much be longer than the key, we repeat that key over and over again until it matches the length of the message. So we write apples, apples, apples all the way to the end, and repeatedly. Yeah. Next, we align this repeated key with a plain text message. Space is big, blah, blah, blah. And each letter of a plain text is then shifted by the amount from the alphabet according to the corresponding letter of a key. Like for example, if a key is A, then the shift is 0. If it's B, then the shift is 1, and so on. And by doing so, the plain text is transformed into the encrypted message shown below. So for example, if you take a look at the first letter, A is 0, right? So 0 plus the letter S is basically the letter S. And the second letter, P, is, I don't know what it is, plus P, and then basically mod 26. Basically, the addition is exactly the same as that in RTX and fine cipher. Yeah, because the shift changes constantly based on the repeating key, the Vigenère cipher is much harder to break than a simple Caesar cipher. Mostly because you don't know the key length. So that's assume that you don't know the key is apples, and you only see the bottom cipher. Then you have no idea what the key length is, right? So the most important thing about Vigenère cipher is that you need to figure out what the key length is. Yeah, another way to think about the Vigenère cipher is that it is basically many Caesar ciphers combined together. So each letter of a keyword determines a different shift, right? Which means that different parts of plain text are encrypted using different Caesar style rotation. Like if a key is apples, then the first letter uses a shift from A, the second uses a shift from P, the second uses a shift from P, and so on. Then the plain text repeats, and the key also repeats across the entire message. Because the shift keep changing, this makes the cipher much stronger than RTX cipher. However, if we know the key length, then we can chop the cipher by the key length and turn it into a matrix, like what we have done right there. Each column can be thought of as a RTX cipher because they are encrypted by the same letter. And in our case, this will be K0, the first key, right? But this raises an important question, like in reality, when we try to break Vigenère cipher, we don't usually know the key length. So we need a mathematical way to determine what the key length is. And fortunately, there are several algorithms to do that. And one of the oldest one and the most reliable one probably is called the Kosinski examination. So the core idea of Kosinski examination is that sometimes, by coincidence, the same word of the sequence of a letter appears more than once in the plain text. So if the repeated word happen to line up with the same position of a key, then we will be encrypting that using the same key letter. And when this happens, the result is that identical group of letters will appear in the ciphertext. So let's take a look at an example on the slide here. So we can see that the key A, B, C, D is repeated across the entire message. And assuming that our plain text is crypto is short for cryptography, then we can see that there is the word crypto is repeated, and it happened to be aligned with the ABCD key that we provided. So notice that the highlighted portion of a text, since the key and the repeated text is aligned, it will end up with the ciphertext containing the exact same sequence, CS642, right there. And this type of repetition can be pretty useful for cryptanalysis. So like if an attacker notices repeated pattern in the ciphertext, then they can make sure that the distance between these two texts can help us determine the key length. Because the length of a repeated pattern must be a multiple of a key length. Like for example, in our case, the difference between the two CSASTP is 16, which will be a multiple of 4. So if we're trying to find the greatest common denominator, the greatest common divisor of all of these sort of texts, then we can probably get the key length of the Vigenère cipher. In practice, we usually find several repeated sequence in the ciphertext. And however, there's an important limitation to the consistency examination, is that if a message is really short, or if a key is quite long, then there might not be enough repeated pattern to analyze, making it much harder to detect the key length. But fortunately for this assignment, the ciphertext that we're working with is pretty long, and that the key is pretty short. So in fact, you can find them nearly like 100% of the time. So the consistency examination works pretty well in our homework. All right, after we have successfully recovered the key length, then the next step is to break the ciphertext into matrix that we have just mentioned before, with row size equal to the length k. This reorganization allows us to turn the Vigenère cipher into a columns of Caesar ciphers. So basically, once you know the key length, you are essentially breaking multiple RTX ciphers and then smash them together. Okay, so now we're basically like treating each column as a RTX cipher we can analyze independently. But now there is a question about this technique. Since each column is encrypted separately, so if we take a look at the first column, it doesn't form a meaningful English words, which means that the log likelihood method that I've just mentioned will not work here, because the log likelihood method requires your text to be meaningful English words. And yeah, so instead of looking for readable words, we need to examine the letter frequency distribution of that column. So in English, certain letters appear more frequently than others, right? Like the letter E, letter T, and so on. And so in order to make sure that our decryption text is correct, instead of looking at the word corpus, we instead look at the distribution of the column. And the resulting text should follow typical English letter frequency pattern. And we basically just choose the one that will make the letters frequency pattern matches English the most. Okay, so to measure this, we use a pretty famous test called the Pearson's chi-square test. So has anybody heard of chi-square test before? Yeah. So it'll probably be taught in like statistic 101 classes, right? So basically, like the chi-square test is a statistical method used to compare the observed data with the expected data and to measure how different they are. It helps to answer questions like, does my data matches what I would expect? Yeah, so the core idea is that for each of a column, we try all 26 possible shifts from 0 to 25. And for each possible values, we decrypt the column and compute the chi-square value. And the formula of a chi-square test is right there. Here, the OI is the observed frequency for data I, and EI is the expected frequency of data I. So basically just sum over OI minus EI over EI. And in our case, the OI is the number of times that appear in the column of a decrypted text. And EI is equal to the expected frequency, which will be the total number of character length times the English frequency of letter I. After computing the chi-square value, for all 25 shifts, we select the key letter that produces the lowest chi-squared value, not the highest. Remember that. And the lowest value indicate that the decrypted text matches most closely with the expected English letter distribution. And we repeat this process for every column from j equals to 0 to key length minus 1 independently. And then we basically just combine the result to recover the full plain text. Yeah, so any questions regarding Visioneer cipher?
Wait, just one more time. Like, EI is like what the characters of text?
The expected frequency for the letter I. So I is a letter.
So is it like you're going to take like individual column, then you're going to take like candidate key as a column, and then you're going to like decrypt using this key, like the specific column. Then you're going to check like the frequencies of the specific column using like the decrypted values.
Frequency of a specific key. So we're trying all the possible keys.
For each column.
Yeah, for each column, and for each column, and for each of the key, it will generate different chi-square value.
Mm-hmm.
And we basically just pick the key that will generate the lowest chi-square value. Mm-hmm.
Okay.
Yeah. All right.
Oh, sorry, I kind of missed out. What do you mean by each column?
So right here we can see that if we know the key size, we can chop the original text into this matrix, right? And because for each column, we're using the same key to perform RTX cipher on it. So like, for example, the first column, the S, S, U, O, I, all the way to the bottom are all encrypted with the same key letter, to be more specific. So basically, we're trying to enumerate all of these keys and pick the key that will generate the smallest chi-square. And we do that for every column. So like, for example, for the first column, we can try A, and then we calculate the chi-square for S, S, U, O, I, blah, blah, blah. And then we can try the letter B. If it's a letter B, then all the letter will be shifted by 1. So S will become T. The second S will also become T, and the U will become V. And then we just perform chi-square on the T, T, V, blah, blah, blah. And then we do that for all possible keys, which is A to Z, right? And then whichever the key will generate the lowest chi-square value will be the target key.
Okay.
Yeah.
And I might be misinterpreting this, but does that assume that the distribution of characters for like the given position? Oh, I guess it's division. Okay.
Yeah. So like the distribution of English text should be the same across each column, right? Because we assume uniformly distributed.
Right.
So the whole distribution of the entire text should be the same as a distribution of an individual row or individual column, or like, whatever, however you pick it. Yeah.
Oh, so it's our assumption, right?
Sorry, what?
It's our assumption, right?
Yeah, it is an assumption. Yeah.
Like, because like you see on one slide you said like, because like column is not like English text.
Yeah.
Like, because you said like column is not going to follow like frequency distribution of English.
No, what I mean is that the column doesn't form English word. Like, if you look at the first column, it is SSUOI. This is not an English word, right? But the distribution will be in English because the full text distribution is in English. So if we pick the first column, then the distribution will also be an English distribution.
Okay.
Yeah. And for the second column, it should be the same. And for the first row, it should be the same. And if you pick like if you pick like prime number of location, then the distribution should also be an English distribution. Yeah. So this is a core idea. Instead of looking at the word itself, we look at the distribution. Yeah.
So would this be the same thing as just like if we use the key for like the first n characters and find the distribution for that rather than to do the column method that you just described? Would it lead to the same result?
Can you say that again? So.
Like, you would just apply the key to like the first n characters and see the distribution for that, rather than to, as you said, list them in columns and then choosing the first.
Yeah, theoretically, but the problem is that the key for the first letter and the second letter will not be will not be the same, right?
Oh, right.
Yeah. So we're focusing on the the characters that are encrypted with the same key, so that we can fine-tune that key and then find those chi-square. So that's why we decided to look at the columns instead of the rows. If we look at the rows, it will be quite easy, right? Because we can just make sure that, because a row will probably form an English letter, but the column will not. Yeah, yeah. And yeah. Any more questions about Visionary cipher? So you get the idea about why we're focusing on frequency as opposed to English word log likelihood count. Does that make sense to you? All right. Okay, so here are some of my tips. So I mentioned Kasiski examination, but there's also other way to do that, like fragment tests, and you can definitely do that as long as your attack work. Feel free to do so. And if you don't like chi-square tests for some reason, you want to use other tests like KO divergence or cosine similarity, you can also do that, because I'm pretty sure that these methods will also work. If you want to get the English letter frequency distribution, here's the link. So you don't need to calculate it yourself from the text corpus. You can just use the one found on Wikipedia, and that is good enough. And finally, I want to note that the key length in this assignment will be 6 to 11 characters. And so this is pretty small. So actually, you can just brute force that, but
Can you lose it?
actually, yeah, you can, but better not do that, because that will also grade your homework based on how you implement it. Yeah, so please implement Kasiski, please. Okay. Or fragment, if you would also want to. If you're like a more savvy math person, you can definitely implement fragment tests. Yeah. All right, now let's take a look at the final cipher, which is the substitution cipher. So substitution cipher is a pretty classic encryption method where each of the alphabet is replaced with another letter. And the key is basically a random permutation of the entire alphabet, which means that every letter will appear exactly once in the key. And this ensures like a one-to-one mapping from one letter to another. And to encrypt the message, we basically just look up each letter's position in the original alphabet and then replace it with the corresponding letter in the key. So here's an example. So we're mapping A, B, C, D, E, F, blah, 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 to QWERTY, blah, blah, blah. So assuming that the text is Gray Fox has arrived, then we'll basically just replace G with the corresponding letter. And in our case, this is U. And replace R with the corresponding letter, which is K in our example. And we basically just do that for the entire plain text. And you will get the encrypted ciphertext from the substitution cipher. Yeah. So basically, this is like a letter changing game. So the mapping is pretty consistent through the entire message, and which means that once a key is chosen, every occurrence of the letter is replaced the same way, right? So like, for example, for the text Gray Fox has arrived, the A in the gray and the A in has and the A in the arrive are all mapped to Q, the letter Q. And this is important because this makes the frequency analysis possible, because even though the characters are changed, the frequency is exactly the same. So this tells us that the frequency analysis can be used to break substitution cipher. But the problem is, how do we perform the frequency analysis? And I'll get to that later. Yeah, but one problem with it is that the key space is pretty large. So the key space is 26 factorial, right? Because we're doing permutation for the key. And 26 factorial is like 4.03 times 10 to the power of 26, and that is 89 bits of entropy. And basically, like any entropy higher than 60 bits means that it is not crackable. It'll take forever to crack the cipher, even though you have all the computational power on Earth. You will not be able to do so. So brute forcing is probably not the stuff that we want to do because it will definitely lead to nowhere. So let's talk about the AI search algorithm, the traditional sense of AI search algorithm called the hill climbing algorithm. So has anybody heard of hill climbing algorithm? Yeah. So if you take like maybe at 540 or something, like intro to AI, you'll probably encounter this stuff. So basically, hill climbing is a heuristic search algorithm. It is primarily used for optimization problem. So basically, it starts with an arbitrary solution. In our case, this is a random permutation of a decryption key. And then it repeatedly makes some small changes to the key. And let's check if the new solution is better according to some heuristic function or scoring function. If it's better, then we keep that key. Then if it's not, then we discard that key. So yeah, we continue this process until no neighboring solution can help us improve the heuristic or the score. Yeah, so basically this algorithm is suitable for problems where we can measure how good a solution is using a clear criteria. And most importantly, when a small change is applied to a solution, we can gradually improve the score. And that's part of the reason why it's called hill climbing. So the diagram right there shows the essence of this algorithm. So we start from a random position, which might be under the mountain, and then we randomly step forward and see if we are at a higher altitude. If we're at a higher altitude, we stop there and then continue on. And if we're not, then we look for other directions to step. And then we continue this process until we reach the summit. Yeah. And the main advantage of this algorithm is that it is really fast compared to simulated annealing or like genetic algorithms. But it has a weakness. The algorithm often get trapped in a local maxima or minima. So if it encounters like a plateau or a basin, then it may get stuck there and fail to continue on to find the global maximum or minimum. Yeah, like the Spirit rover, which gets stuck in the crater on Mars. Yeah. Yeah. But for solving substitution ciphers, the hill climbing algorithm works reasonably well. And the reason is because that many nearby keys have smaller scores. So when we slightly change the key, like for example, swapping 2 letters, then the decrypted text usually changes only a little. As a result, the score does not change randomly. It changes smoothly and gradually. Also, like a small improvement are often detectable. If like the new key produces a text that looks more English-ish, then the scoring function will reflect that improvement. And because of this, gradual changes can move the solution toward the text that look more English-ish, which means that each swap that is successful will bring the decrypted text closer to the original meaningful English sentence. And you can get the plain text by that. Yeah?
So I'm kind of confused on the steps. Is it like, are we guessing the first letter of the key and then?
We're not guessing. We're actually generating a random key and then swap the key and test if that swap key make it better. If it does, then we'll continue doing that process. We'll keep the key and continue that process. And if it does not, then we will try again.
Just that letter, or are we randomizing everything?
No, just swap the letter for each test. And we'll get to that later. I'll show you the exact algorithm of how you should implement that. Yeah. Yeah, and this method works surprisingly well with for breaking substitution ciphers. Yeah. Yeah, so this is the algorithm that so this is a basic cracking process. Yeah. First, we generate a random key. We can do that by shuffling a fixed alphabet like ABC all the way to Z. Just do a nut shuffle on that. And then we randomly swap letter in that key. And after each change, we can check whether the new key will improve the result based on some scoring functions. So when the decrypted text is getting close to a meaningful English plain text, this means that we have a higher score. And if it doesn't generate meaningful English plain text, you'll have a lower score. And the entire procedure can be repeated T times, and T stands for the number of tries. Because maybe like the key space is very large. I mean, in our case, it is large. And so multiple attempts will help us explore different possibilities based on the initial permutation. So in our analogy, this will mean that the initial point can be in different parts of the like lower points. Yeah. So yeah, this is everything about the hill climbing algorithm. And I hope this is pretty straightforward to understand. Yeah, you initialize a key, and then for n iterations, you swap two letters and check if you're getting close to your plain text. Yeah, that's pretty much it. So any questions regarding this algorithm? Yeah.
Question, like, if you are going to find out that like you are going to swap two letters and it's going to improve the result, like what should you do?
So for this homework, the problem is that you should automate everything, right? So in normal setting, you stop when the plain text is what you want, and you hit Control C. That is a normal setting. And in this homework, like the designer of this homework is Patrick, and Patrick wants you to automate. Yeah.
Hey, I'm just notifying y'all that this room closes at noon.
All right, yeah, we'll finish before 8:15. Yeah, yeah, all right. Yeah, and basically Patrick wants you to like automate everything. So we need to do some hyperparameter tuning, which I'll get to that later. So we can see that the orange stuff right here, like the fixed initial key and the number of iteration and the number of tries are all hyperparameter, right? So we need to like fine tune these hyperparameter to make sure that we can automate everything. And I'll provide you some hyperparameter at the end, which you can use to make your homework better. Yeah. So basically, in normal case, it is a sort of trial and error, because like hill climbing isn't a exact algorithm. It will only find a solution that is good enough. Yeah. And for this reason, that's the exact same reason why I'll give you partial credit if you're not partial credit. I'll give you full credit if your generated text, recovered text is good enough. Yeah.
So if we keep swapping
Mm-hmm.
when our result is improved, wouldn't we eventually just get to the actual key? Like, is there going to be a scenario where we reach the plain text?
There's a scenario where you'll get stuck in local minimum, but for substitution cipher, this is pretty rare as far as I know. And there is also a possibility that it will get close to the text, but it will not eventually reach there because you just happen to swap the wrong letter. Or maybe you didn't fine-tune your hyperparameter correctly, and it will stop right before you're about to reach the summit.
At that point, can you just manually swap, see which ones work?
You can, yeah. This is actually what happened in CTF problems. So all we need to do is run this algorithm and get a good enough text. And maybe there's some letters that are off, and we just fix that manually. Yeah, but for this assignment, Patrick wants you to automate everything, which is a pretty darn thing. But it is possible to, make your attack work like 99.99% of the time by tuning the correct hyperparameter, which I'll get to you in the next slide, I think. Yeah. Let's talk about some hyperparameter tuning. And we can basically set the initial key to A, B, C, D, E, F, G, all the way to Z, and then perform knot shuffling. And if you don't know what knot shuffling is, you can take a look at Wikipedia. It's pretty straightforward. There's only like 6 lines of code. Basically, just shuffle the text uniformly. And for the algorithm, the try number T, you can set it to 4. Because hill climbing can often get stuck in local minima, so we need 4 times of tries to find a solution. And you can also set the number of iteration to like 8,000. This controls how long each run of the algorithm searches. And more iteration now allow more opportunity to allow us to refine the key and improve the score. But it will take a longer time. So my experience is that 8,000 iteration is good enough. And if for some reason that these hyperparameters doesn't work on your case, then you can basically increase the number. Increase from 4 to 6, increase from 8,000 to 10,000, whatever. You can definitely do that. But it will take a longer time to run, but it doesn't matter. We will not evaluate your homework based on performance. So, yeah. It's definitely okay to set it to a higher value. Another question is that how do you measure whether your text is English-ish enough? And I've already covered this in the RTX cipher and the fine cipher. Basically, just use the same log likelihood sum for your score, and that should be good enough. And also feel free to use other algorithms like simulated annealing as your solution. It's sort of overkill to use that for this homework, but if you want to do that, feel free to do so. And yeah, that's all I want to say about substitution cipher. So any questions about this one?
I
Yeah.
still understand the algorithm
Uh-huh.
computation. Let's say you are going to solve 2 letters.
Mhm.
You're going to find out which choose right now.
Uh-huh.
How previous iteration is going to influence next iteration?
Can you repeat the last sentence? What? Yeah.
How previous iteration is going to influence next iteration?
This. Say that again. What?
You have current iteration.
What iteration?
Iteration.
Huh?
Iteration.
Yeah, iteration.
And you are going to swap letters.
Uh-huh.
And then you are going to see if it is going to improve result.
Uh-huh.
How is going to influence next iteration?
Next, how do you implement next iteration?
I think you just keep swapping.
Just keep
until you
swapping.
get a higher score.
Yeah.
So it's like a completely randomized swapping. If the swapping improves the score, then we keep the swap, and then we keep moving on.
Yeah. Basically, that's.
Oh, okay. I see.
Yeah. Maybe I can show you guys the pseudocode at the end if you still have a problem. And I can explain what this is doing.
No,
Yeah.
I understand.
Yeah, because this is a pretty straightforward search algorithm. But if you're not familiar with traditional search algorithm, then this might be. When I first learned this thing, it was pretty hard to understand. Yeah, but once you get it, then I think you'll get the essence of it. Yeah, it's exactly the same as how you're going to climb a mountain. You try to step forward or step to the right or step to the left. And if you step to the forward and you're at a higher altitude, you stop there and then keep doing that. And if you're at the lower altitude, you go back and then try a different direction. Does that make sense algorithmically? All right. Okay, so last thing I want to talk about is AI stuff. So you're going to implement something in C, and you may sometimes run into bugs. And in those situations, it may be helpful to just ask ChatGPT for help, or any other LLM, like Claude, DeepSeek, Gemini, or whatever. But note that you need know that our course has a pretty clear AI policy, and just follow it strictly. So basically, all policy regarding to asking for help, including LLM, requires citation. So is it acceptable to ask for help when you're stuck? But you're not allowed to copy and paste vibe code generated stuff directly into your homework. Remember, and most importantly, remember to ask citation in your homework, saying something like, hey, ChatGPT or Gemini, help me on this part of homework, something like that. And yeah, you should never just copy and paste your solution directly from code generated by these AI. But you are allowed to do certain amount of vibe coding, like help me generate the algorithm in C for hill climbing, whatever. Yeah, and it will generate a template for you, and you can just modify stuff in the vibe coding generated code to accommodate for the requirement that I told you. Yeah, most importantly, just remember to cite your ChatGPT or Gemini or whatever for whichever part of homework that it helped you. Yeah, that's all I want to say about vibe coding. So yeah, any questions? Oh yeah, we finally make it through before 8:15. Yeah. If you have questions, you can definitely ask me. I'll stay around for like 15 to 30 minutes. So if you have any questions, feel free to reach out to me. Thank you.